Thank you for joining our first webinar in our four-part Open-NFP fall webinar series. Today, Vyas Sekar is going to present scalable and robust DDoS detection via universal monitoring. A copy of the presentation, archived replay, as well as any project code will be made available shortly after the webinar. These, as well as our previous webinars, can all be found on the classroom page on the open-nfp.org website. Open-NFP's objective is to support and grow reusable applied research and technology development in data plane network functions processing. We do this by focusing on reducing the barriers to performing research in this space to researchers and developers creating, implementing, and verifying their ideas on production networking hardware. Open-NFP supports research in a wide range of technologies, including software-defined networking, OpenFlow, Open vSwitch, and P4. We support researchers with a variety of tools, including deeply discounted hardware, IDE software, and cloud access to development systems and direct support from our engineers in a research community. We also provide support to learning advanced networking concepts on our hardware through tutorials and seminars, such as the one we are performing today. We encourage proposals to research funding agencies. Vyas Sekar is the Angel Jordan Early Career Associate Professor in the ECE Department at Carnegie Mellon University, where he is a part of the Sci Lab. His research interests lie at the intersection of networking, security, and systems. He received his PhD from the Computer Science Department at Carnegie Mellon University in 2010. He earned his bachelor's degree from the Indian Institute of Technology, Madras, where he was awarded the President of India Gold Medal. His work has been recognized with the NSF Career Award, the ACM SIGCOM Rising Star Award, the NSA Best Scientific Cybersecurity Paper Award, the CSAW Applied Security Research Prize, and multiple Best Paper Awards. Over the last few years, we have seen a substantial increase in the type, scale, and sophistication of distributed denial of service attacks. A first step to any DDoS mitigation strategy is the need for accurate and robust detection mechanism. Traditional techniques have either relied on Netflow-style sampling or the use of custom sketching-based monitoring algorithm, but result in undesirable trade-offs between fidelity and generality. In this webinar, we will describe our early experiences in using an alternative approach building on the recent promise of universal sketching and implementing this using P4 and the Netronome platform. We invite you to join the 50+ universities and companies working directly with Open-NFP through projects. Please stay tuned after the webinar for a special Open-NFP announcement. Thank you, and over to you, Vyas.
All right. Thank you for the introduction. I hope people can hear me clearly. All right. So the work I'm going to present today is in collaboration with colleagues at Johns Hopkins who've really been sort of pioneering the theory behind universal monitoring, and several students both at Hopkins and at Carnegie Mellon. And the work is really, as sort of the intro mentioned, on how we can do really large-scale detection of distributed denial of service attacks. So to give you some context for the work, really I think we've seen over the last few years that DDoS attacks or distributed denial of service attacks have gotten really worse. Maybe like 5 years ago, things like a 10 gig attack or a 10 gig SYN flood was what people were worried about. But these days we are talking about like terabit scale attacks and many different diverse types of attacks. New kinds of SYN floods, new kinds of amplification attacks, IoT-based denial of service attacks, and so on and so forth. So that the bottom line we see is that sort of these DDoS attacks are getting worse and increasing in number, their sort of scale, and in the diversity of attack types that they use. Now, sort of an essential component of any defense strategy against these DDoS attacks is to first be able to detect that the network is under attack. And of course, as we see, there are many different kinds of attacks. So what we see is like this, there's sort of many different diverse types of attacks. And for each of these different kinds of attacks and different attack strategies, we need to write many different custom detection algorithms. For example, you may want to see which IP addresses are sending a lot more traffic, which IPs are sending a lot to a particular destination. Is there an asymmetry in packet counts or SYN counts across different directions to a destination, and so on and so forth. So you can think of like every kind of attack has its own custom logic for detection and time series analysis and different kinds of really sophisticated algorithms. So one natural question is, so how are these kinds of detection algorithms supported and realized in sort of modern networks? Sort of the more traditional approach, and this is what a lot of companies do, is based on sort of implementing these strategies on top of traditional Cisco's Netflow-style sampling. So the idea is packets come in, you sample packets at random, typically say 1 in 100 or 1 in 1,000 packets, and then you sort of collect these flow reports based on these sample packets, and you estimate whatever metric you want, say the distribution, the SYN counts, or whatever you want, like the questions I asked earlier, on top of these sampled flow reports that you've received. So this is the sort of the classical DDoS detection workflow that many production systems are using today, and there are many companies built on top of it, like Arbor and sort of Prolexic. All of these are sort of built on top of these kinds of capabilities. But unfortunately, it's actually very well known that these kinds of coarse-grained sampling techniques are actually a very bad fit for the kinds of fine-grained analysis and anomaly detection algorithms that we want to do for security capabilities, especially in anomaly detection algorithms. So consequently, there's actually been a lot of interest in the research community on developing what I call very sort of application-specific algorithms. So, and there was a lot of interest in developing what are called the sketching or streaming algorithms. And at a high level, what they do is, if you can tell me the metric you want, I want to say count the sources that are sending the most amount of traffic, or I want to capture the entropy of a particular distribution, or I want to figure out some super spreaders or whatever, give me a particular metric. It turns out we can actually write custom algorithms that take a small amount of memory. These are approximation algorithms that can, with a small amount of memory, are able to sort of estimate these metrics with high accuracy with a very small amount of memory. And this is really nice capability for monitoring, in the sense that with a small amount of CPU and a small amount of memory, you can get very accurate estimates of the metrics you want to get. And indeed, there are sort of a ton of these algorithms if you look at the networking and the databases literature on custom algorithms for different kind of queries you want to write. Now, this is really cool from a theoretical point of view, from a sort of an academic point of view. But really, if you think about the practice, it's actually a really terrible idea. And the reason is that every single anomaly detection algorithm or DDoS attack that you think of will need to have a custom application level sketch, a custom data structure, a custom hardware packet processing component, a custom algorithm, and so on, which seems like sort of an expensive development effort, because you have to develop these algorithms and hardware for every single algorithm. The second thing is also increases the complexity of your data plane. If you have like 100 different algorithms, are you going to implement sort of 100 different capabilities on even on a programmable data plane? And third is actually an even more fundamental problem, that often when you're doing these attack detections or anomaly detections, you actually don't know ahead of time what you're looking for. Whereas in these architectures, there is a tight binding between the data and the control plane, meaning that I need to know a priori and pre-deploy the algorithms I want to implement in the data plane. And the control plane can only estimate those metrics. If I want some other metric, say some new metric for detecting DNS amplification, now all of a sudden I don't have the data, I don't have the counters for doing that. So this is sort of stuck in this world where I have these cool algorithms, but they are not really practical. So this brings us to sort of the driving question for our work, is that today there's this fundamental disconnect. You can either have a general algorithm like Netflow, or you can have these high fidelity sketches. So it's like an exclusive war. You can either have generality or fidelity, but not both. And sort of the driving question for our work is, can we move away from this exclusive war world into sort of an and world? Can we have generality and fidelity at the same time? And if you can do that, that would be a game changer in the network monitoring world, because you can now have a general purpose and high fidelity algorithm at the same time. Okay, so now given that context, there's several open questions, deep technical questions in the space. One is, well, this is kind of a holy grail of network monitoring, and in theory, does such a construction actually exist? So there's even an existential question of whether we can actually do this in practice. There's a question of whether it's competitive with respect to custom algorithms, right? In terms of the memory versus accuracy trade-off, is such a universal or a general purpose approach going to be as efficient as a custom algorithm? Is it feasible to implement in modern hardware like Open-NFP type appliances and so on? And there's also a question about how do you do it sort of system-wide deployments of these in a whole network and so on. So this sort of is going to be the roadmap for this talk. I'm going to focus on does such a construction exist? Then I'm going to talk about the other questions one after the other. Okay, so going back to the question of does such a construction exist? And this is where sort of we build on this really cool breakthrough from the theory community called universal sketches. Now, to understand what a universal sketch is, so I need to go into a little bit of the math to explain what a universal sketch is. Now, so here's a framework for thinking about any streaming algorithm. So in a streaming algorithm, you typically have a stream of length n. So think of these as packets. And each of these items has like some unique ID. Like the ID might be 1, 5, 3, 2, 4, 6 or something. And typically the way you're computing these metrics is you want to say, the classical streaming algorithms compute what are called frequency moments of these things. So imagine each item I has a frequency or a count. So in this example stream, item 1 has count 4, item 5 has count 2, and so on. So you have a frequency vector. And you can think of the metric that you're estimating as being like a frequency moment, which is really summation I equals 1 to n over each of the unique IDs, sum fi to the k, where k is the kth frequency moment. So, and this is a classic framing of the sketching problems in the theoretical community. Now, what we're asking is actually something called a universal streaming algorithm. That is, rather than know the frequency moment fk a priori, can I compute an arbitrary g function, g of fi function? Okay, so you might say I want like g say f1 plus f2. I might say f1 squared plus f2 squared, f1 cubed plus f2 cubed, and f2 cubed, and so on, or f log f, or any such arbitrary function. Can I do an arbitrary g function? And that's the sort of the theoretical question that universal streaming is asking: is can I do an arbitrary g function with a single sketching data structure? And the surprising result. This comes from the theory of universal streaming, and I'm not a theory person, but this is a really cool theoretical result, is that there is indeed such a construction. And the theorem shows that the theory shows that you can have a universal sketch construction that can estimate these G sums with a single universal sketch using sort of polylogarithmic. Again, polylogarithmic just means that in terms of the number of items and the size of the stream, you're keeping sublinear amount of memory. You're keeping a really small amount of memory to maintain the data structure. So imagine you're processing like at line rate 40 gigabits with millions of flows. You're not keeping millions of megabytes of memory in your routers. So that's really the nice thing about these sketching algorithms. And in fact, it shows that it also sort of scopes. This is theorem 1. It kind of scopes the kinds of estimates or queries for which this is feasible. So it sort of says that as long as this g function has some properties, which it does not grow faster than fi squared, you can actually estimate these functions in polylogarithmic memory. Okay, so that's sort of the theory of universal streaming. I'm happy to point you to the papers, but I actually do want to move into the sort of the system side of things quicker. So, and the intuition sort of really comes from a way in which it is constructed. So you can think of like sort of two cases. One case where there is a single large heavy hitter, like say one source that's sending a lot of traffic, and the other case, there is no such source that's sending a large amount of traffic. In the first case, you can use a traditional heavy hitter algorithm to find that, and then you're done. In the second case, the intuition is that, okay, even if a single large heavy hitter doesn't exist, we can do the sort of a recursively sampled approach, where you iteratively sample substreams of smaller size, and you find these heavy hitters on these sort of sampled substreams. Okay, again, this is the intuition behind why the theory works. And again, I'm going to sort of punt on this and say that there is some strong intuition on why this is a good idea, and there's actually empirical evidence for this as well. And I'm going to move on. So what does it look like? The construction look like in practice? It's actually pretty simple. So what you do? So imagine you have this stream of packets coming in. So we're going to use sort of a sampling stage, or a sort of a sampling stage where we're going to use like log n hash functions, and we're going to sort of sample each hash function basically says, do I pick this ID or not? So at level 1, we have picked IDs 1, 5, and 2. In level 2, you're hashing that again and saying, I'm going to pick 5 and 2. In the last stage, you're picking only the ID 2. So it's like a sort of a recursive subsampling of the stream to create logarithmic number of streams. Again, this is why the theory works. So this is sort of the basic construction. And what you do is, for every such level 0 through log n, you keep what is called a standard L2 meaning the L2 norm heavy hitter algorithm. So there are well-known algorithms for doing this. Count sketches are a classical way of doing this. So then what we do is, having kept these counters, then we report at every level the heavy hitters and the counters. And then there is a very simple sort of algorithm that can then estimate the G-sum on top of these, the sketches that you're keeping at every level. So think of it like I'm having a Bloom filter at every level, which is also keeping counts. And I'm merging these Bloom filters to estimate the G-sum after the fact. Now, the key behind universality or the generality here is, I do not need to know that particular G function ahead of time. And that's really the key idea here, is that in a traditional sketch, I need to tell you exactly what function I want. I want like summation f or summation f squared. In this model, I don't need to know what that function is. You can tell me the function much later, right? After you've collected these counters, you tell me what function you want, and there is this delayed binding between the counters and the function you're estimating. And that's the sort of that's where the generality or universality comes from. All right. Now I've told you the sort of the theoretical basis for it. So how do you envision actually realizing it in like a modern router or any kind of data plane? So here's a sort of a mapping of the theory, the data structures, onto an actual, say, data plane. So imagine you have a router that's in your data plane, and you have a control plane that's running the application-specific computations. And again, the key is the data plane does not need to know what the applications or the control plane wants to estimate. So there is some configuration from the control plane, and as traffic comes in, the data plane is keeping these samples. Then it's creating these sketching counters using the hashing logic I mentioned earlier. Then it reports the top k possible keys that it has seen back to the control plane, and the control plane then does the app estimation. But notice in this workflow that other than some sort of very generic configurations from the control plane, I do not need to know what app 1 to app n are when I'm implementing the data plane algorithms. So that's sort of a nice mapping between the universal sketching theory and an actual network realization. Okay, sounds good. So hopefully, I mean, again, I'm condensing a whole bunch of research into this couple of slides. I'm happy to point you to the papers, both on the theory and the systems side, to tell you what, to give more details. Feel free to ping me at the end of the talk. So the next natural question is, okay, now we've answered the question that, is there a feasible construction? So the next natural question for us is whether this universal sketch construction is actually competitive, meaning that is it as accurate, is it as efficient as if you wrote like a custom sketching algorithm? And this is where we did a sort of extensive trace-driven evaluations to evaluate universal monitoring against a wide range of custom algorithms on a variety of traces. So the setup was actually described in our SICOM 16 paper, but I briefly talk about it here. So we took several sort of backbone traces from CAIDA. So these were collected at different OC 192, OC 48 links. We split these traces into like small epochs, like say 1 second, 2 second, 1 minute epochs. And we vary the amount of memory that we give to these different algorithms. So you can imagine Universal Sketch has like 600 KB of RAM versus 5 megabyte of RAM and so on. Again, just in terms of evaluation, we tried 3 canonical sketching applications. One is a standard heavy hitter formulation, which is to identify the 5-tuple flows that consume more than a fraction gamma of the total capacity of the link. A change detection algorithm that tries to identify flows that contribute the most to the traffic change. So imagine in the first 5-minute interval, flow 1 was 100 kbps. In the second interval, it was like 1 gigabit per second. So this is the largest change in the flow rates. And finally, we also look for sort of the DDoS victim ID, where we suppose we know the destination of a particular website. We actually want to check whether it has been in communication with more than k unique sources, which might be sort of a standard signature of somebody under a DDoS attack. Okay, and the reason we picked this is because we had like open source implementations of the sketching algorithms for these from the literature. And in fact, there's a sort of another work called OpenSketch that has implemented many of these algorithms. All right. So I'll show a couple of different results here. So the first result here on slide 16 shows that universal monitoring is indeed competitive. So the setup for this is we take several traces. So we have like trace 1, 2, 3, 4, 5, 6 traces here, different OC 192 links from CAIDA. And we have these 3 applications: heavy hitter, change detection, and DDoS ID detection. On the left, we see the error rate for universal monitoring. So the error for the different application, think of it as like a false positive rate or a false positive plus false negative rate for the application. And on the right-hand side, we're actually looking at the custom sketches for each application. So we wrote a custom sketch for heavy hitter, custom sketch for change, and custom sketch for DDoS. I mean, of course, the result makes universal monitoring look a little bad, but the takeaway is that it's not that much worse, right? You really have an absolute error of like around like 3% compared to a 1% error. But the key here is we're actually only using 600 KB in total, whereas in the custom sketches, you would need to keep 600 KB per task. So we sort of fixed the total amount of memory given to the algorithm. In one case, universal monitoring, in the other case, custom sketches, and we compare the error rates for the fixed amount of memory. And the takeaway, it seems like it's actually competitive. The error rates are actually not that much worse than if you wrote a custom algorithm for each application scenario. So that is the good news for us, that okay, there is actually this can be practical, and universal monitoring can be competitive with respect to custom algorithms. So this was actually a very positive result. Going in, we knew the theory, but we didn't know whether it would actually translate into practice on realistic traces and so on. Now that's it. So the real benefit is on the next slide, and this is sort of a hypothetical evaluation that shows the true benefit of universality as we change or grow the number of applications, right? So in the previous case, we sort of did a standalone evaluation of one application at a time. But in reality, if you're monitoring a network, you have like sort of a portfolio of different estimates and applications you want to run. So what we evaluate here, again, it's a very simple evaluation that shows as the portfolio increases, but with the same amount of memory, what is the difference in error between universal sketches and custom sketches? So we start with simple app set of size 1, where we're only running heavy hitter, then we add the DDoS, and then we add the change detection. And the interesting thing is actually, you'll see that the error gap will switch over from the positive side to the negative side. So it's a gap between universal monitoring minus the OpenSketch error. And you'll see that, okay, it starts off being positive. The universal sketches is actually worse on each application basis. But as the number of application grows, you actually start to see the benefits of universal monitoring, in that you suddenly start seeing for the entire portfolio, it's actually a much better option than if you look at each individual application in isolation. And that to me is the biggest win from universality, is that you can sort of aggregate the resources and give it to one good primitive rather than fragmenting it across multiple different algorithms. And that's the power of the generality that universal sketching gives you. Okay, so this is sort of the two things together tells us that universal monitoring is competitive, and sort of more importantly, as if you think about making this future-proof, this is actually a future-proof algorithm, because it actually does better as your portfolio grows going forward. All right, so we have two more questions. So the other questions I want to focus on is it actually feasible to implement on sort of modern NFP platforms? And we did two experiments here. One is we actually did the original thing we actually implemented using P4, and we've also done some preliminary work implementing it on top of the Netronome platform as well. Okay, so what I'm going to describe is some of the experiences in implementing it on these platforms. Hopefully that sort of there are some generalizable lessons from our experiences for other people using these platforms, as well as sort of it can hint at what capabilities should there be in these future NFP data plane platforms. All right. So here's what sort of the workflow looks like. So recall that we had like these four capabilities: sampling, sketching, top K estimation, and the app estimation. So typically what's running in the data plane are sampling, sketching. Sampling and sketching have to run in the data plane. Now we do have we will run app estimation in the control plane. It doesn't make sense to run it on the data plane because the data plane does not know what it is. But there is indeed a subtle trade-off here. So we can, and the nice thing is sort of things like P4 give us abstractions to implement things like hash functions and registers. So we did find a mapping between this workflow and P4 to sort of implement it. That's it. We did have a sort of a design choice that we needed to make here. And the design choice was the following: that should we implement the top K stage in the data plane, or should we defer that to the control plane? And the trade-off here is that for implementing something like a top K, you need like a priority queue implementation in the data plane, which we speculate might be hard in hardware. Yeah, it might be wrong. On the plus side, the storage and communication overhead is actually small because you only need to report the top K to the controller. Instead, what we did in practice was we said, okay, look, the communication cost is not that much more. It's only like a few megabytes. So we would rather send you the raw counters and do the top K estimation in the control plane itself, rather than go through the pain of trying to implement this priority queue in the hardware itself, in the data plane. So in fact, that is the realization for P4 that we had, where sampling and sketching run in the data plane, but the priority queue algorithm actually runs in the control plane, and we just take the hit of sending a few more megabytes of these raw counters into the control plane. And that's a conscious trade-off that we made. So that was our P4 implementation. This was from our SIGCOMM 16 paper, where we showed that indeed there is a feasible mapping of universal sketches on the sort of at that time the 2016 version of what P4 offered. So looking forward, we actually got sort of a couple of the Netronome NICs, and we were actually looking at how to implement the same workflow on the Netronome platform. So the initial attempt, we thought, and this is like sort of the lazy approach, we said, okay, hey, look, we already have the P4 code. Why don't we just like take the P4 code, and since P4 to Netronome already has some capabilities, we just like directly port it. But we sort of found these limitations of doing this translation via P4. One was that it would quickly run out of space. Just the mapping was not very efficient. It didn't really fit in the NICs. It didn't have this sort of loop statement. We had to unroll these loops, and it became unwieldy. And also, it sort of lacked expressiveness, right? I mean, in the sense that we had to store these seed values for the hash, and then every time we realized that P4 did not have that capability, we had to do like some hacks, or we realized we could not actually do it in practice. So this was step one. Again, unfortunately, the students spent a lot of time trying to figure this out, and then eventually said, hey, look, this P4 thing sounds cool in theory, but maybe it's not the best way to implement universal monitoring on Netronome. Okay, so that sort of led us to the second implementation direction, where we realized, okay, look, you can actually do the micro C, exploit the micro C capabilities of the Netronome IDE to implement the universal sketching workflow, and that turned out to be much more powerful in terms of the expressiveness of the capabilities and sort of exposing these capabilities directly. Again, there's some time spent in understanding the APIs and also figuring out where the performance bottlenecks were. We did use the simulator, which is actually very useful later on, as once we realized there was a simulator to profile the bottlenecks and understand the bottlenecks and say, okay, then figure out alternative implementation for those bottlenecks. And interestingly, and this is kind of was a surprising result for us, we realized that when we implemented the Netronome, the universal monitoring on Netronome the first time, a significant chunk of time was spent in the hash computation. And I think the reason was something like the modular operation is not a native operation, and it's kind of implemented in a weird way on the platform. So we sort of spent some time sort of re-changing the hash function to say, suppose we didn't use the modular hash function and we actually use the shift operation into the modular operation, how much does the throughput improve? So the results here show sort of the benefits of going from the traditional modular hash, which is what we had used all along, to the shift-based hash function with a 32-bit key and so on. So, and you'll see that there's actually a substantial, as a number of, we can actually go from, say, 25 gigs to almost like sort of 40 gigs, up to like 5 universal monitoring sketches. We can get line rate with the modular operation, but not with the traditional, with the shift operation, but not with the traditional modular hash function. Okay. And again, this was a surprising result. I mean, we didn't expect this to be a bottleneck, but this was like a surprising bottleneck. So if there is indeed a native hardware hash function, chances are you wouldn't have to go through these hacks. Now, one trouble with this, we actually realized, again, these are our takeaways from this, is that the shift operation is much faster. We thought that there would be some issues with synchronization and how these counters are updated when we did this parallelized across the cores. But it turns out some of the atomicity capabilities that the platform provides, the atomic engine actually did a great job. So we actually did not have to spend too much time engineering the correctness and the consistency for when we move to a parallel world. That said, there is still a limitation of this in the sense that the shift operation is not a very good hash function. For these sketching things to work, you actually need some rigorous guarantees on how good the hash functions are, and the shift function is not particularly suited for those guarantees. So we sort of have been trying to implement these other kind of sort of faster hash functions that have been known in the theory and practice communities. So one is something called a tabular hash function for implementing these kinds of things. And we've been trying different variants of this tabular hash function to see what can actually fit in memory and so on. So we realized that we cannot do a 64-bit hash function, but we can do a 32-bit, and it takes around 200 megabytes of memory to fit in there. So, but again, that's a lot of memory on a data plane. But at least we know it's feasible in the current hardware. All right. So, and we do have some preliminary results by using the tabular hash function. The y-axis here shows the throughput. The x-axis shows these different tricks that we had to try, and we tried to have different kinds of numbers of sketches. Like we had 3 dimensions: source port, destination port, and source IP. Of course, as the number of dimensions grows, the throughput grows down. But we can do with these tricks. We feel we can support like around 2 to 3 dimensions at sort of full line rate on the platform. So that's sort of where our sort of preliminary implementation results are. Now, okay, going back to, I said, I promised you some experiential lessons from this. So one of the things we actually did realize the simulator helped us a lot. It sort of really sped the workflow of the student in terms of understanding the bottlenecks and then figuring out what the right strategy for optimizing it. So the simulator seems like a useful thing. Maybe it is obvious to people who have worked with this platform before, but it was sort of a nice lesson for us. And the other thing is actually that sort of the micro C environment has a lot more flexibility and seems a lot more powerful than the P4 based implementation. Again, I don't want to say this is generally true that you should all use micro C instead of P4, but in this specific application scenario where we really needed to go to low level optimizations, the micro C frameworks seem to have a big win over the P4 based approach. And also, so on the positive side, the good news for us was we could show at least sort of a preliminary version of universal monitoring. It's feasible on the Netronome platform with 3 dimensions and the 5-way independent tabular hash function. Again, to the best of our knowledge, nobody else has tried to implement this on hardware, and we think that's pretty cool. Okay, so one last thing that people often ask us is like, so all of this, I'm talking in the context of a single router or a single switch. So one natural question is like, okay, how does it extend to a network-wide setting, say in a data center or in an ISP scale deployment and so on, right? So typically in a network-wide setting, you have like multiple paths, multiple dimensions of interest. So you may want source IP, destination IP, source destination combinations, and so on. So how exactly does this approach generalize to a network-wide setting? So we do have some preliminary thoughts and ideas on that. So here's the sort of the network-wide problem formulation. So imagine you have a network with different routers, and you have like different sort of end-to-end flows, say from origin O1, origin O2 to destination D1 to D2. So you have like sort of say 2 origin destination flows, and you have say different dimensions, source and source destination that you want to monitor. So a naive solution is to basically replicate every sketch for every dimension on every node, right? So that's sort of the naive solution is to use D cross N switches, sketches, or universal sketches, one for each dimension on every node. Of course, that is sort of a wasteful use of the memory on the data plane because you're replicating a lot of work. So what our goal instead was to say, can we use a far fewer number of sketches? So the memory consumption of a network as a whole is small, but at the same time be able to provide what I call a one big switch abstraction. That is, the effect of monitoring the network as a whole is equivalent to monitoring all of this traffic going through one single massive tap. And if you give that abstraction, it's easy to write applications downstream. And sort of we did come up with a sort of a solution where we sort of use a clever way of coordinating the sketches across these different network-wide nodes and placing them intelligently to avoid duplication such that we can provide this one big switch abstraction. Again, in the interest of time, I'm going to skip that, and I can point you to the Sekar paper that talks about that. Cool. So that's kind of what we did. So where are we right now? So I do want to tell a little bit about where we are going with this work. So it's still sort of, I think there's a lot of exciting opportunities in this space. So one thing we do want to do is write suitable compilers or APIs to write monitoring queries on top of universal monitoring, right? So say, for example, you want to write a new monitoring application. How do we translate it into the capabilities that universal monitoring has? That still requires some effort and understanding of universal monitoring, and we want to abstract it out away from the monitoring applications themselves. The second thing we actually want to do is actually we've been prototyping several canonical DDoS detection applications and showing that there is a nice mapping between what the DDoS world is doing for detection and the universal monitoring capabilities. And that's it. So, I mean, there's still a lot of work to be done on the performance side. So we're continuing with our profiling, benchmarking, and implementation exercises, and also experimenting with other platforms like Open vSwitch, FDIO, and other things to look at to better understand what does it take to implement these kind of sketching algorithms, especially universal sketching, at very high line rates with low CPU consumption and things like that. All right. So I think we are pretty much done. So just to conclude, so DDoS detection is a hard problem. It requires a lot more flexibility and programmability from the data plane. Today, we are stuck in this world where you either have general monitoring or flexible monitoring, sort of general or sort of high fidelity monitoring. What we want is sort of have both. And this initial promise of universal monitoring is sort of shows that it's actually feasible, accurate, and it's possible to implement. And there's a whole bunch of open questions in terms of improving the performance, not bound APIs to write these applications, and prototyping actual applications, and so on. I think that's all I had for today. I'm happy to hand over, take questions. I think Bapi had some announcements at the end. I think I'm done. Any questions?
Actually, there is one. And in terms of northbound APIs, do you see that it's a new API or some way to insert yourself into some existing set of standard APIs like OpenFlow or P4's northbound API?
So I think this would be a custom API for monitoring. Like I don't think P4 or not OpenFlow actually has anything for monitoring or writing these monitoring queries. So think of it like, so imagine that I give an API for an operator to write like a SQL query, right? Count sources that have sent more than 10 unique packets in the last 5 minutes. So that's kind of the northbound API I'm talking about. I don't think sort of any of the P4 or the OpenFlow people actually have thought about monitoring. In fact, for most of these things, monitoring is a sort of a second-class citizen. They're not designed for monitoring as first principles. So to the best of my knowledge, they don't have northbound APIs for monitoring. And that would be sort of an interesting direction to go into. And then it can inform what those northbound APIs for them needs to be as well.
So a northbound API at the network level, not at the level of the individual monitor.
Correct. Yeah, think of somebody writing in the control platform, the application queries, and that's the kind of northbound API I'm talking about.
Okay, very nice. If there are no other questions, oh yes, there is. Will this become more feasible if hardware-based hashing is available in the data plane?
Oh, absolutely. Yeah, definitely. And that is something we see that, look, a lot of the work we did trying to improve the performance was working around the fact that we didn't have a good hash function. If there's a hardware hash function that has these properties that sketches want, I think that would sort of dramatically improve the performance and not have to do all these like hacks.
Is a sketch-friendly hash function different from a regular hash?
Somewhat. For these sketches to work, I think there's like there's this theory of like sort of min-wise independent hash function, two-wise independent hash functions. Again, each of these sketches require different properties. So one way to think about it is, yeah. So typically there are these things called like three-way, four-way independent hash functions, and what you want for many of these theorems to hold. The theory to hold is that each of these things will require a particular type of hash function. I think for the universal sketching, we need a five-way independent hash function, but that's kind of what we would need in the hardware.
Is there a relationship between the quality of the hash function and the size of the error band, or it's not a predictable, clean relationship?
I mean, the problem is, I think for the theorems to hold, I think you do need that. In practice, these things do a lot better than the theorems and the worst case bounds suggest. But I think for the theory to hold, that is, if you want these approximation guarantees and accuracy guarantees to hold for arbitrary workloads, you do need those kinds of hashing capabilities. So again, like for example, even the shift hash function works pretty well, right? But the problem is, I could, as an adversary, construct a workload that will make it completely, the accuracy bounds go completely haywire. I think that's the trouble. And if I can't reason about how good the hash function is, then the theory and the practice may not necessarily match.
Okay. And one question about the implementation: did you and your team switch completely from P4 to micro-C, or did you use micro-C actions inside P4?
I think we gave up on P4.
You gave up on P4. Okay.
Yeah.
Okay. Any other questions?
I mean, we may revisit it, but I think again, yeah, at least I mean the student decided that okay, look, it's more pain for me to work around the limitation. Like the P4 code when it compiled didn't even fit in the NIC, right? So I'm like, okay, look, rather than try and reverse engineer why it's not fitting in the NIC or why the memory consumption of that is too much, we are like, okay, might as well move to micro C.
Got it. Okay.
So it was like stuff. It becomes a black box at that point. Right? Then we also need to reverse engineer what your P4 to platform micro C compiler is doing, and so on and so forth. And that was not a good use of our time.
Yes, actually, that's a nice segue into the announcement. I'll just do an announcement and come back to any questions with Professor Vyas here. Our group is actually pretty happy to announce that we're going to release, we're releasing NFP SDK 603 for the Open-NFP audience. The two new features are that we have support for Mac-based timestamps and the ability to match headers beyond 256 bytes in a packet. There's also some more ability to fit larger tables that we don't specifically highlight to address some of the problems you just talked about, Vyas, and also reduce the host memory usage by the RTE. And so if you're in OpenNFP and you have access to the SDK, you should have immediate access to 603 and be able to download this new update. And the other thing that we've done in this update is gone off and compiled a whole bunch of externally available P4 sources on with the Netronome toolchain. So we will publish a list of the compatible, or the open source code that has been compiled with this SDK. Look for an announcement on the OpenNFP mailing list. Okay, Professor Sekar, thank you. If there are no more questions, I'll hand it back to Carly.
All right, thank you, Vyas and Bobby. This webinar will be made available shortly on the classroom page of the OpenNFP.org website. Thank you all for attending.